the October edition. Thanks for coming. Hope you're going to enjoy the presentation tonight. Big applause for Cloudera for providing the venue and the beer. They're going to be pizza. Thanks. They're going to be pizza later on, so stay with us. And also, two important notice. One is like the meetup is only in this space, so please keep the boundaries untouched. And they're going to be, second thing, they're going to be an office visit between the two presentations. So hopefully we're going to have really good lights to the city. Hope you're going to enjoy. So they're going to be like a 10 minutes office visit between the two talks. And the pizza will be just after the second talk. So hopefully it's going to be all right. Oh, so first presenter, János. I met him like a year ago. He seems to be a very capable and very cool person. Thanks for applying for this presentation. I think there are going to be a lot of interesting thoughts to that. I just learned an interesting fact of János. Apparently, he was born with 24 fingers.
I don't have any.
So it's a bit creepy and weird fact, but please welcome János, a superhero.
All right. Help me tune this thing. It's turned on, right? Can you hear me all right? Is it too loud? No? It's okay? All righty. So, welcome. Thank you for having me. I'm very excited to be here. My name is János, and I work as an infrastructure engineer at Meltwater in the engineering enablement mission. To give you some context, what is engineering enablement? It is a mission created within the company to support its 350 plus engineers over 50 plus, in 50 plus teams over 20 locations. We're 3 engineers in the US and 5 engineers in the EU. And support means that we enable teams to accelerate without thinking too much about infrastructure, allowing a rapid path from ideation to prototype to providing business value. We provide a number of centralized infrastructure services like telemetry, meaning metrics, logs, monitoring and alerting, as well as container orchestration solutions. We also support teams in moving out from the co-located data centers to the Amazon cloud. A little bit about the company to give you some more context on top of that. Meltwater is the global leading media intelligence platform. Our software combines the power of AI with the largest news and social media database in the industry to bring our clients advanced media monitoring, social media listening, social media management, PR analytics, and influencer engagement tools. To give you a 1,000 or rather million-mile view of what our system looks like, we have this picture. You have internet, the big cloud on the left. We have crawlers and fetchers that gather data from various sources all over the internet. We run that data through a enrichment pipeline and then a storage pipeline and store the data into various databases and search engines. And on top of this, we build APIs, and on top of those APIs and using these APIs, we build advanced tools like analytics, applications, dashboards, notification functionality, and so on. That's enough about the company. So what is this talk about really? Well, it's about this. It's about a log message, an event. Actually, not just one, but many of them. And it's about how our team evolved its system design to go from this to this, and then this, and eventually this. But it's also a story about massive bug fixes, capacity limits, bad resource allocation, timeouts until failure, and sudden data surges. For example, turning on trace logging inside a critical loop in a data processing cluster. And if teams do that, it will lead to this picture. So this is from Kibana. It's showing log volume per application. Each different color is a different application here. And the graph actually goes all the way. Unfortunately, you can't actually see it, but current time is here. And you can see that there's data missing here. And the teal color guy is being naughty because they turned on trace logging, and now they're being the party pooper, and they're fucking up the system for everyone because the logs are being delayed. They're sitting in a queuing system somewhere, millions of them. And when you do this, it makes our system feel like that. And it makes our on-call engineer feel like this. And then there's finally this picture. It's a graph showing overall data volume in our production cluster over time from 2017 August until 2018 September. It's going from around a couple of hundred gigabytes a day to a peak of around 4,500, 600 gigabytes. In concrete numbers, on average, our production cluster, one of three, is doing 3,800 gigabytes indexed with replicas, 1.7 billion messages per day, individual messages. That comes out to around 40,000 messages indexed with replicas per second. And we have a 32-day rolling retention in Elasticsearch. So how did we evolve our system design to cope with ruthless clients, massive amounts of data, and unpredictable traffic? Well, we inherited a system. I will quickly skim through the initial couple of steps in the interest of time, and then focus on some larger, more exciting challenges. So for starters, we have the usual suspects. When it comes to a system like this, we have syslog on the left, responsible for gathering data, and then forwarding to Logstash, and then we have Logstash, the L part of the ELK stack. Logstash is responsible for data ingestion and data processing. And then we have Redis in the middle, responsible for queuing. And then we have Elasticsearch, ES, the heart and soul of the entire thing. It is the storage and the search engine that provides most of the functionality. And then, of course, there is Kibana to the right. This is the rich UI that we provide. Well, it's not like we provide it. It's part of the ELK offering. But it is what all clients use. When it comes to Elasticsearch, as I said, it's the heart and soul of the entire thing. So a little bit of intro. Elasticsearch is a distributed system. It's a cluster comprised of nodes. And on nodes, data is stored in search indices. And those search indices are broken up into index shards to distribute the load. And those indices, those shards can be distributed over multiple nodes, over a cluster. So when it comes to our use case, we start out with this. We have a single Elasticsearch node in an Elasticsearch cluster, and in that Elasticsearch cluster, we have a single index, well, a daily index, because we just have the one index, and it ends with a date part that actually resolves our current day. So each midnight, we roll over to a new index. So this is how we start out. This is our current pipeline. And the first evolution step comes with us realizing that syslog is actually not appropriate for us anymore. For one, the data it sends is not structured. Number two, there's a size limit on the length of an individual log message that it can forward. So that's no go going forward. So we implement a next generation receiver here, Logstash component, all the same. And that receiver, next generation receiver, opens up a TCP port where applications can stream JSON data directly. So that's all fine and dandy. On the Elasticsearch side, we have to add more nodes. So we take that logstash index, we split it into 2 shards, bring that guy over there to the left, add a second node, and move the second shard, the orange one, to the second node. So we basically double the throughput of our Elasticsearch cluster, and this way we can keep going until we have capacity in our data center. Back to our pipeline, this is where we're at. Next up, we have more and more applications starting to use the system, starting to use the new next generation receiver. So we realize that we need to solve multi-tenancy in our database, because the more applications there are in that single index, the higher chance we have of fields colliding that different applications send. So to solve that, the multi-tenancy problem, we implement a next generation indexer. Logstash all the same, except this indexer will put data into separate indices in Elasticsearch that look like that. So now the index name contains the application name. Each application gets its own index, basically its own database with its own schema. So now there's no chance of fields overlapping within the same index. And also this provides better scalability for us on the Elasticsearch side, because not all, the entire data for a given day is not within a single index, but in many more manageable pieces. Back to the pipeline. This is where we're at. Next up, we deprecate the old pipeline. We don't want to deal with syslog anymore and the old receiver and indexer part. And as our next step, we actually have a need to have third-party application logs in the system as well, meaning databases, spewing systems, search engines, and so on. So we bring FileBeat into the mix. FileBeat is part of the same ELK offering developed by the same guys, the same company. It's a simple log harvester that just reads the log file and forwards it to the Logstash. So we hook that up to the receiver, call it the multi-receiver, and then the more data we have, we realize we're having scaling problems, but not in Elasticsearch, but actually the Logstash, the processing components. So we have to deal with that. To deal with that, we move Logstash into containers, and move those containers onto a Mesos cluster, a container orchestration solution, to take advantage of a dynamically orchestrated environment, so we can better configure the applications themselves, the number of instances that we need to run, and the amount of resources that we give them, CPU, memory resources. And we also implement a dedicated parser component here. Before, we needed to do only a little bit of parsing because applications sent JSON data directly that was structured. But now, with FileBeat into the mix, we need to parse Apache logs out, Elasticsearch logs out, RabbitMQ logs out, right? And parsing previously was done in the indexer, and that's not good because the indexer needs to do I/O work, not processing. So to separate concerns, we implement the parser and surround it with queues, so everything is nicely decoupled. And it's actually a bug that kickstarts the fun part of our journey. So if you zoom in on this part, applications talking to a receiver, the data has to travel on the wire somehow. We need to serialize that data and deserialize that data before processing. And it is the codecs that take care of this part. We have 2 possible codecs that we can choose from in this setup. The JSON lines codec. The JSON lines codec is basically reading new line delimited JSON stream until end of file. And we have the JSON codec that is basically reading until new line. So what happens if the client expects JSON and the server expects JSON and the client sends JSON lines? Right, the application creates a batch of messages, right? New line delimited neatly. and send it over, and the server reads until new line. And then it's done with the batch of messages. So basically, in this, if this is the case that the client sends, we lose 3/4 of the data. So that's not great. Let's fix that. Let's fix that and deploy that to production. And this is how our deployment looks. In high traffic use cases, where the application has a higher chance of creating larger batches, it can lead to a difference of 10 or even 20 times as much data. So you can see the report match store component was logging around 40,000 messages per 30 minutes, and it went to above 800,000. So that's nice. That brings us to our first challenge. The first challenge is that we're having massive Elasticsearch scaling issues. We're having capacity problems, as in we do not have more capacity in the data center. And what we already have is uneven. All those Elasticsearch nodes are running on spare hardware. And we also end up in an allocation catch-22 problem. What this means is that because we have uneven nodes in the cluster, uneven as in disk size and disk throughput, we have to add allocation rules onto the Elasticsearch cluster, meaning we add rules to specify which nodes can contain which indices and which nodes cannot contain certain indices. And the catch-22 part of the situation is that without allocation rules, we run out of disk on certain nodes, while other nodes have 6 terabytes of data, 6 terabytes of disk free. But if we add allocation rules, we end up with an uneven cluster. And that looks like this, basically. This is user CPU over our 5 Elasticsearch nodes. You can see here that there are 2 of them that are basically not doing anything, while one guy is really working hard. That's perfectly visualized by this heat map, this allocation heat map. The columns you see here are the Elasticsearch nodes. The rows are the indices for different applications for a given day. The darkness of a cell in the matrix denotes how many shards that specific node has out of the given index for the row. So you can see in the middle, there are some nodes that do not have any shards on them. No wonder they're not working, right? And you can see here in the Elasticsearch row that only one node has all the shards for it. So that is probably the yellow guy here, right? So how do we solve that? Well, we figure we build a new Elasticsearch cluster, and we do that in AWS. Thankfully, it is at this time that the company says that, hold up, we need to migrate from the co-located data centers out into the cloud. That is the future. And our team capitalizes on that opportunity, and we figure we move the entire thing to AWS and use that opportunity to build a new cluster, upgrade the entire stack to newer versions because we were lagging behind by quite a bit. So easy peasy. With that out the door, on to the next challenge. Well, it's not actually that easy. So how do we actually do that? Well, we figure we can build an entirely new Mesos cluster in AWS. This is in order to minimize the amount of changes that we have to do to the system. And it is actually our team that runs the Mesos cluster, the container orchestration environment in the data center. So we have the knowledge to build a new one and run it. So we can build a new one for us in AWS, and we can build a new and shiny Elasticsearch cluster, and then send data to both places. Then we can cross-compare between the 2 clusters if we want to validate that all indices have all the same data and the late data looks the same way. So how do we do that migration? Well, we don't move the deprecated parts of the pipeline. We don't care about that guy. Move that one up there. and we build an identical copy of the entire thing in AWS. From then, we can fork the incoming stream, the unprocessed incoming stream, implement an uploader component that creates files on disk and uploads those files to S3. And we can hook up a Lambda function to S3. Lambda can trigger on object created and object modified notifications from S3. Basically, we can trigger a run whenever a file is being uploaded. And in that Lambda function, we can take the contents of the file line by line and push it to Redis. So using this approach has a number of advantages. It's actually pretty fast because it does batching on this part. The uploader creates files that are batches of 5 megabytes, configurable, of course. It has the advantage that it's scalable. Both S3 or Lambda are extremely scalable. It's also very fast because we're doing batching here, and upload is fast over there. And we get a couple of things for free. We get replay functionality for free, and we get stream backup functionality for free because everything is there in S3. So replay, meaning that if we want to reprocess something, if Elasticsearch blows up, we can just replay from S3. We trigger the Lambda functions. But there's also another advantage since we assign unique identifiers upon receival to every single log message that we get. Everything has its unique ID when it reaches S3, so there will be no duplicates if we need to reprocess something, if we, for example, modify the parser to have more advanced parsing rules. So when we do that, it looks like this. At this point, we have around 30 to 40 Lambda invocations per minute, and they're processing between 200,000 and 400,000 lines per minute, pushing them, all those lines to Redis, and average Lambda invocation time is around 7 seconds. And when we have completed that, we can deprecate the unused parts, the legacy parts of the old pipeline, and we can finally remove it and decommission it. And on to our next challenge. Well, we're having Elasticsearch hotspots. What does that mean? Well, it looks like that. There are some nodes that are working way harder than all the other ones. But I mean, why? We're supposed to have a new shiny Elasticsearch cluster that is even running on the same nodes and all that. So why is that? Well, the problem that we need to solve is that these hotspots are causing indexing backlogs. Nobody gets their data, right? So why is that happening? We think that it is due to us having an uneven distribution of indices to nodes. Not all nodes have the same amount of data, same amount of indices for today. And when we receive a data search, for example, then obviously we can't cope with that. So let's fix that by certainly not doing anything manual, for example, moving indices around for a month or two, maybe. But actually, the solution is to not run the system at 85% capacity. Who knew? By literally, this time only, by literally throwing money at the problem, we can solve it, because it actually leads to a better distribution of indices to nodes. And it looks like that. Much better picture than what we had before. On to challenge number 4. Surprise, surprise, Elasticsearch hotspots. This time, due to a little bit different reason. We have, after some analysis, it turns out that we have an uneven distribution of index sizes. Not all indices contain the same amount of data because not all applications produce the same amount of logs. Meaning that some indices have too much data for the amount of shards that they're broken up into. And Sadly, the number of shards is hard-coded in the system, and exceptions are added manually in configuration. This is how the problem looks. On the x-axis, you have, for a given day, index sizes for different applications. The two graphs are the same data. The one on the top is linear scale. The one on the bottom is logarithmic scale. There is a single application that is logging more than 700 gigabytes a day, and the second one, not even 100. So it's pretty uneven. So let's fix that. Our solution is to try and right-size the indices when we're pre-creating them for the next day. We can use historical data, analyze historical data, see how much data, how many logs certain applications produce going back a couple of weeks, and then we can try and create indices with the right amount of shards for them. This is from design documents that we have for this. For the index for tomorrow, we can look back 1, 2, 3, and 4 weeks in the past, and using simple linear interpolation, you can try and figure out how big tomorrow's index is going to be. So unfortunately, I do not have any images or graphs to show how things changed when this was introduced, but overall it was pretty good. We achieved better distribution overall on our cluster. There's no more need to manually size indices, and using this approach, organic data growth is followed decently well over time. On to challenge number 4. Well, this time it's the queuing system. It's Redis that is not appropriate anymore. So Redis is actually an in-memory database. It's not actually a queuing system, and it shows. It's inherently single-threaded, and as I said, it's not a queue. So when we need to fork the stream, for example, what I mentioned, pushing data to 2 places, the data center cluster and the Amazon cluster, we need to duplicate the data, as in literally create 2 Redis lists and push the same data into both. Because in Redis, once you read something, you actually remove it from the list. And on top of that, Redis is not a proper distributed system. It's kind of hard to scale already, but when it comes to the list use case, it's even harder. This is the part I'm talking about. Since both S3 and Lambda are massively parallel, a replay event can easily overwhelm the single Redis instance that we have for the entire pipeline. And when we figure we're close to Redis's limits and run a small performance test to see how much capacity we have in the system, not much. You can see where our test kicked in. This graph is showing the blue line is average Lambda execution time, and the yellow bars are max of the same metric. Meaning that when our test kicks in, it's nobody that can talk to Redis anymore, because Redis is single-threaded. Redis is receiving data from the network on that single thread. So when we launch 500 Lambda functions, Lambda containers at the same time, all of them wanting to talk to Redis, well, nobody can talk to Redis anymore. So that's great. What do? Well, we move to Kafka. Compare Kafka to Redis. Kafka is actually a majorly disk-based system compared to Redis being mostly in memory. Kafka is thankfully multi-threaded, much more suited to our use case, and it's actually an append-only log, meaning that you have a topic and you keep writing to the end of it. And you don't remove data except when it phases out of retention, But generally, when you read the data, you don't remove it, right? So it's much more appropriate for our use case here that there's one guy that writes the thing, and any number of consumers can come in and read the same data as long as it's there, and they don't remove it. And they can do so with the reading with little to no overhead. And Kafka is a proper distributed system, meaning that we can scale it. Alrighty, so this is where we're at conceptually, simplified pipeline. But it's actually not the complete picture. As I mentioned, we have Lambda writing to Redis, but we also have this guy over there. So I mentioned that we have backups of the stream in S3. We have backups only of what comes from the data center through S3. We don't have backups of the data that comes in through the AWS-based receivers. So we need to back that up and implement an archiver component, the same one as we had before, reads from Redis, pushes to S3. So again, we have to duplicate the entire stream here. And we also have an exporter component. Again, it pushes to S3. The only thing special about this one is that one of our teams came to us and said that they would like some of their data, some of their logs exported to an S3 bucket of theirs. So the exporter is doing some filtering on the entire stream and pushing it to S3. And again, we have to duplicate the entire thing, right? And this is all a single Redis instance. That's a lot of duplication for a single instance. And when we introduce Kafka, this is how the picture changes. Not a lot. Conceptually, we have, instead of two Redis queues, we have 2 Kafka clusters. The archiver moves to the right of the first Kafka cluster, reading the exact same topic as the parser, and the exporter does the same thing with the indexer, reading the same topic. The 2 clusters are actually not the same this time around. They have separate concerns, and we have named them differently accordingly. We have the intake and the exhaust cluster. So let's dive into that a little bit. So the intake cluster has to be fast and safe because it has data that's not been backed up yet. And its consumers are mainly CPU focused. While the exhaust cluster needs to provide a huge buffer for Elasticsearch to sluggishly do its job. When we have a data surge coming in that Elasticsearch cannot deal with, our queuing system needs to be able to bridge that time while Elasticsearch catches up. So we can afford to have fewer nodes on exhaust because all of its data has been backed up at that time. So we don't need that high of a replication. And on intake, we need more nodes. And on intake, we need small and fast disks, while on exhaust, we can afford to have slower but huge disks. As I mentioned, we need higher replication on intake, but can afford lower replication on exhaust. And when it comes to numbers, this is what we ended up with. EC2 nodes on both sides. Intake is using i3 X large nodes, the IO focused ones. They're the ones that have ephemeral NVMe SSDs mounted on them, 0.95 terabytes, and we use 3 of them with Kafka applications up to 3 with 48 partitions per topic. The exhaust cluster is using R4 X large nodes, the memory focused ones. They actually have the same CPU and the memory configuration, but disk is vastly different. R4s have external EBS volumes mounted to them, the SP1 types that are built with stream processing in mind. So that's just perfect for our use case here. And we need 6 terabyte volumes mounted to each. And we have 2 of those, set Kafka application to 2 and 48 partitions per topic, all the same. Since then, we have to double the instance count to 6 and 4. But with the 3 and 2 configuration with our performance tests, this is what we saw. we went to 14 million messages processed per minute. We thought that number was pretty good to stop with the performance tests. Same event, but more focused, metrics more focused on the parser itself. Remember, the parser is the one that sits between the intake and the exhaust cluster. So you can see here that consumer lag eventually, initially it grew, but eventually started going down when we tweaked a setting or two. You can't really see it, but we're running with 24 parser instances at this time. And when we finally tuned the settings, they're pretty capped on CPU itself. So meaning, you know, we could have added more parsers, but we figured this was enough. So 14 million messages per minute, that comes out to 233,000 messages processed per second. It's a pretty good number. And we will still bottlenecked on consumer CPU. We could have added more CPUs, more consumers. And our metrics showed that the Kafka setup that I showed you before, can still do much more just with those instances. And after that, can still scale. So we could have added, could have doubled the consumers. And after that, we could have added more Kafka nodes. And after that, we could have added more partitions to the same topic and then added more Kafka nodes and then added more consumers and just scale and scale and scale. So with the fancy new queuing system, now that it can take a beating of around and above 200,000 messages per second. Next up, it's the indexing that has to be on par with that. So remember this this problem, and we turn on trace logging. And this problem, when there is one application, an application cluster that turns on its trace logging and sends us more and more data. And we need to deal with that. So our final challenge is that it's very hard to react to data spikes on the Elasticsearch side, and indexing falls behind. So what do? Well, we figure we can use Elasticsearch index aliases and use a rollover API to work around the problem. What does that mean? Well, this is the part I'm talking about to visualize the solution. Let's blow it up and look inside Elasticsearch. Right. So this is where we're at, right? We have in Elasticsearch, we have this one search index, logstash myapp 2018-06-06. And we have the indexer coming in and saying, hey, please index this document into logstash myapp today, which is 2018-06-06. So the cluster does that very happily. And we have then Kibana with the user coming in, executing the query. Kibana essentially saying, hey, please search logstash myapp star, star being the wildcard here, search logstash myapp star indices that have data for today. When that happens, Kibana fires up the search and lets the system figure out what indices what are the indices that we need to search in. And that query resolves to that index for logstash myapp 2018-06-06. And you can see here that we have a single index with 2 shards. Those 2 shards are located on 2 separate Elasticsearch data nodes because we have allocation rules that specify each individual shard of an index needs to be located on different nodes. So when we do this, there are only 2 machines working at any given point in time. When there's a data spike that comes in for my application, I turn on trace logging for my application. This means that we can't scale out. And essentially, we have to wait until the next day passes, midnight passes, that we create the new index for tomorrow with more shards to have more processing power. So that's not great, because what if I do this at noon? and I'm basically trapped in this crappy situation for the next 12 hours, and that's not cutting it, right? So what if we introduce a layer of indirection with index aliases? I can set up an index alias that has the exact same name as the index before, logstash myapp 2018-06-06, and then point that alias to a weekly index. And the weekly index looks very similar. We have logstash myapp in the beginning, and there's 2018, 23 parts for the dates, and 23 is actually the week number. And then after that, we have an ordinal on 6 digits. So when we do this, indexing still works just the same, because the indexer is saying the same thing. That name still exists. It's an alias that resolves to a backing index. And search still works all the same, because the exact same expression still works all the same. Due to the wildcard, it resolves to an index, and we can still figure out which indices have data for today. So if we do this, and we have a data search that comes in for myapp, we can call the rollover API on that name, and we can post some settings overrides to the name, basically the alias that eventually resolves to an index. And when this happens, what Elasticsearch does is it creates a new index, takes whatever the alias is pointed to, takes that name and increments the ordinal from 01 to 02, but applies the settings overrides, meaning that it creates the new index with 8 shards. And since we have the allocation roles set, this means that this index now is distributed over 8 worker nodes. There are 8 nodes working now instead of 2. And indexing still works because the alias is there, and search still works all the same because the wildcard now resolves to both indices, and our pre-flight search still works, that figures out for my given time frame which indices need to be searched. Is it the first one, the second one, or both? So that's pretty good. And our tests say the same thing. When we initially started our tests, we had 2 shards per index, the one index under test. And we called rollover to 4 shards and rollover to 6 shards. We essentially achieved on-demand scaling of our Elasticsearch cluster. So what if we have this part, right, that I talked about, and there's also the Kafka queue, Kafka topic that Indexer is reading from. You can have a monitoring agent hooked up to both Kafka and Elasticsearch, gather metrics from both consumer lag information from Kafka, and Elasticsearch index metrics from Elasticsearch, and put it into a time series database. And we can hook up a alerting system to that time series database, and we can hook up a trigger to an index management script. And that index management script can do what I just described before. And if we do this, we can basically have event-based auto-scaling, not only of the underlying hardware of the Elasticsearch nodes, but the inside of the database as well. So we've gone to a billion messages, and this will go well beyond that. My name is János. You can reach out via that email or LinkedIn, and you should definitely check out our engineering blog at underthehood.meltwater.com for blog posts and job postings and more. Thank you.
Very well done. Do we have any questions from the audience? Okay, try to pass the mic. Gentlemen.
Yeah, thanks. Hi, János. It was a wonderful presentation about the scaling issue. I really liked it. My question is, so the lead up to the question is, I saw that you are using dates, and then you introduced using the concept of weeks. Do you use UTC, or how do you manage time zones in this scenario? Especially if a user is looking for today, that's a pretty fluid concept if you're a global company.
Right. Time zones are actually one of my pet peeves. Surprise, surprise, when dealing with time series data. I think there's only one correct answer to that, and it's to use UTC, nothing else. Use UTC, store in UTC, run your servers in UTC, and the niceness well, not the niceness, it's actually the pain of dealing with time zones then is left to Kibana. Kibana figures out what time zone your browser uses and then converts the query accordingly into UTC. Or you can be a power user and inflict more pain upon yourself and use Kibana in UTC as well and do the time zone calculation in your head. Did that answer your question?
Okay, next question. Have you considered using binary formats instead of JSON?
Binary formats. No, I don't think so. It was way easier for everyone to set up JSON, to talk JSON between applications and the receiver, and then to have the JSON format all the same on the wire. It was easier for everyone. So no, not yet. We never really saw the need to use that.
Any more questions? Then I think it's time for the office visit. So,
all right. Thank you again. And if you have any more questions, please come talk to me.